So, hello everyone, welcome back for Lecture 2 of Nuclear Materials with me, Dr. Miles Stouffer. Last lecture we covered the fundamentals of nuclear engineering, including binding energy, types of radiation, exponential decay and half-life, through to the interactions of neutrons with matter, where you all recall the types of interactions you can get between a neutron and various bits of material. Neutron capture, activation, and fission, and how the probability of those reactions depends on the neutron cross-section for said reactions. So today we'll finish looking at neutron interactions and cover a reaction I didn't mention much through won't mention much through the rest of the course: fusion, concluding the fundamentals of nuclear energy. Then we can move on to reactor design, where I'll cover fusion and fission reactor designs, from the very first designs through to the proposed Generation 4 reactors, with the principal components that make up a nuclear reactor and the materials requirements for each. And once that's done, we have all the information we need to really delve into the core of nuclear material science. Thought I'd pop that pun in there. And then we'll begin the second chapter of the course, radiation damage. So, we'll start today on page 15 of your notes, section 1.22, fusion. As I said, I won't cover fusion in detail, but it's worth mentioning just for completeness, really. As we saw in the last lecture, energy is released when a nucleus becomes stable. And it's that energy that we want to transfer into electricity. And last lecture we covered how splitting heavy nuclides leads to stabilization by transmuting to smaller nuclides with a higher binding energy per nucleon. But fusion, on the other hand, stabilizes lighter nuclei by fusing them together, again leading to a higher binding energy per nucleon. And what we're interested in is getting as much energy possible from these reactions. So why are we so interested in fusion over fission? Why is that such a hot topic? Well, one of the reasons is the energy released per mass of nuclide is so much higher for fusion reactions than fission reactions. Now, the most significant reaction to consider when it comes to fusion is the fusion of deuterium and tritium, and that's known as the DT reaction. That reaction yields around 17.6 mega electron volts per event, with a very low Coulomb barrier of only about 0.68 electron volts, meaning it's much easier to achieve. But as shown here in the reaction for the DT, this reaction involves a deuterium atom and a tritium atom, DT, deuterium and tritium. Both of those are isotopes of hydrogen, deuterium having 2 protons, tritium having 3, all with the same number of neutrons, 1. And that fusion results in the release of an alpha particle on the right-hand side of that equation, shown here as a helium nucleus. So you get a release of a helium nucleus and you get the release of a neutron, along with a huge amount of kinetic energy. And that's the energy that we want to capture. Now, a lot of you will have heard of deuterium, but some of you won't. And, well, that's because it's not as common as nuclear engineers would perhaps like it to be. It is naturally occurring in water, but it only makes up around 0.015% of natural water. So to obtain an adequate mass of deuterium requires a huge amount of water to be processed. And here lies one of the key hurdles in making fusion economically competitive. Because to isolate that deuterium, you require something called isotopic exchange, which some of you will have studied. And that's done between, in this case, hydrogen sulfide and just your typical run-of-the-mill water, H2O. And that process is also known as the Girdler sulfide process. where hydrogen sulfide flows through two columns repeatedly, cycles through, with both columns at different temperatures, say 30 degrees and 130 degrees. Now, because of the temperature difference between the two columns, the deuterium can begin to enrich in the hydrogen sulfide in the hotter column and then back to the water in the cold column, enriching it in deuterium oxide. And so that water becomes what we call heavy water. Okay? And it's heavy water because deuterium is heavier than hydrogen. So hydrogen oxide is light water and deuterium oxide is heavy water. And that cycling between the columns goes on until you have around 15 to 20% deuterium enrichment, at which point it's vacuum distilled to produce high purity reactor grade heavy water. Reactor grades greater than 99% pure deuterium. Well, why does this affect the economics of fusion power? Well, that enrichment process is incredibly energy intensive, so weighs quite significantly against the energy you get out of a fusion plant at the end of it. So it has to be accounted for when measuring the energy efficiency, what you put in compared to what you get out for a fusion plant. So you find if you could find a more efficient process by which to produce heavy water, fusion becomes much more appealing. But what of the other ingredient in our DT reaction? We need the T, don't we? Yeah? We've got the DT, we need the T, we've got the D, that's deuterium, we need the T, that's tritium. Well, that doesn't occur naturally, as it's radioactive and it has a half-life of around 12.6 years. So in order to produce the tritium, we need to first fuse deuterium with deuterium. That's called the DD reaction. And as shown here in your notes, deuterium plus deuterium equals hydrogen plus tritium, again with a bucket load of energy, some of which could be captured and converted to electricity, but really what we're looking at now is the production of tritium. So the tritium produced must then be used to produce a DT reaction, and then the cycle goes on with the reactions sort of ideally repeating in a sustained manner. But combining hydrogen isotopes is very, very challenging. And it's much harder to sustain such reactions than, say, the fission of uranium-235. Because, well, first you must overcome the electro-repulsive forces that are repelling those nuclei from one another before it surpasses that and the nuclear forces can bring them together. And to do that, these isotopes have to be fired at each other at great speeds. And how can you get those great speeds? With great temperature. And by great temperature, I'm talking about several million Kelvin. Now bear in mind that the core of the sun is around 27 million Kelvin, so we're trying to achieve something several million Kelvin is not going to be easy. But you need it. But it gets worse with the DD reaction because you need an order of magnitude higher temperature for the DD reaction. Which means that a fusion reactor must first have a supply of tritium produced elsewhere before you can begin to start any tritium production within the reactor. And where do we get that tritium? Well, we get it through bombarding lithium with neutrons. So we manufacture that tritium through radiating lithium with neutrons, as shown in the reaction here at the top of your page. And that leads to some very specific design requirements for fusion reactors. For example, in the blankets of the reactor I'm going to talk about now, where you have to have a sort of lithium blanket, for example, to produce that tritium. Okay. Now there are two types of fusion reactor design: inertial confinement and magnetic confinement. And the diagram you can see here is for magnetic confinement. And magnetic confinement is the more popular. And you may have heard of it referred to as a tokamak design. And that design relies on very strong magnetic fields produced through huge magnetic coils. I recommend you Google ITER to see the size of the reactor they're building there. But those huge magnetic coils, they confine a hot plasma of the nuclear fuel. And it confines that plasma in the sort of iconic torus shape of a fusion reactor, like a donut. Now, in order to get such strong magnetic fields, you're going to require very large currents. And the fields produced basically give the required particle density to get our fuel up to speed for it to fuse together. If any of you have heard of JET at the Culham Centre, just outside of Oxford, or ITER, as I mentioned, the International Thermonuclear Experimental Reactor, that's the method that they use in those experimental reactors. And ITER is an international project in Calarache in France to build basically the first demo plant for future fusion reactors. Of course, the famous saying goes that fusion energy is always about 30 years away. Well, that seems to be holding pretty strong. ITER's behind schedule and is not in the form that the lead scientists probably ever hoped it would be, which is a real pity, as of course fusion is viewed by many, especially young upcoming scientists such as yourselves and engineers, as the holy grail of energy research. But people that have been working in fission for a while can become a little bit embittered. And because of that, I won't really be talking about fusion very much, but let's just cover the last sort of design of a fusion reactor, and that's the inertial confinement reactor. Now, the inertial confinement design, they were mainly developed by the US, though we do have one in the UK. And these reactors are ignited by heating and compressing the outer layers of a tiny sphere of deuterium and tritium. And in the loud, kind of Hollywood-esque way you would expect of our American cousins, they used giant laser beams. Yes, giant laser beams fired upon a ball of nuclear fuel. And what these lasers do is they basically rapidly heat the outer layers of the ball, causing them to explode, seeing huge shockwaves through the remaining interior gas mixture. So the inside is then gas, and it sends shockwaves that compresses these. So much energy is put in with these shockwaves that it's enough to actually induce the fusion reactions and create a chain reaction so that the hydrogen fuel is used to generate the energy. So, why do we even bother? Well, fusion presents the potential for several really key advantages, which is why we've been pushed to do it. Virtually limitless fuel, reduced significant emissions and radioactive waste, and less chance of severe accidents, which is obviously a key concern with nuclear, and warrants an entire module in itself. Now, many grand claims have been made with regards to fusion, and all of these points that I just made are correct, but you've got to be careful not to see fusion as being a sort of truly limitless supply of energy, or truly having zero radioactive waste, or that there is absolutely no chance of severe accident, because there are chances, there is waste, and there is fuel processing that needs to take place. But nonetheless, fusion is an exciting area, full of giant magnets and, as I said, giant laser beams and explosions. So it tends to entice students, especially, into the field, and you really meet some characters in the fusion field. And with that done, I will not speak again of fusion, only in passing. Should you wish to explore the bizarre world of giant laser beams, I will gladly point you in the right direction, away from me. In the meantime, clean and sustainable energy production is really one of the biggest challenges of our lifetime. And in order to tackle it, regardless of your personal opinions, we must call on nuclear fission. So we've seen a quick overview of what reactors look like. Well, what about fission reactors? what are the challenges to materials scientists when it comes to nuclear power? Well, as with many technologies, there are several general considerations we have to take when choosing materials. And these considerations will be referred to throughout the rest of the course with respect to each component present within the reactor that we're going to go through. So what are they? Well, we've got to consider mechanical properties. Is it strong enough? Oh, it's jumped. Is it strong enough to withstand the applied or residual stresses within the component? Is it tough enough to prevent catastrophic failure during its design life? How easy is it to make? How straightforward is it to manufacture a component out of the material? Can it be welded, formed, machined, graphene coating? Could we make it out of graphene? No, I think we'll give that a miss. Dimensional stability. Can a component maintain its operation throughout the life of the reactor? Can the material withstand the high temperatures it's subjected to, or will it creep or undergo phase transformations? Similarly, corrosion resistance. Can the material withstand the environment it's in? Will it react with the reactor coolant? Does it need to be corrosion resistant? And then you look at, okay, well, we got this coolant going through, that means we're transferring heat. So what about heat transfer properties? How good is the material at passing heat from its interior to its exterior, for example? We need to get heat from the nuclear fuel into the steam and out to the turbines. Well, what's the thermal conductivity like of the materials that the heat needs to go through? And finally, how available is the material, and is it cost effective? Platinum pressure vessel decorations? Probably not. I think we'll give that one a miss, thanks Lawrence Llewellyn-Bowen. So those are general considerations. They're not nuclear specific, but they are equally as important as those that are. So what considerations are unique to nuclear? Well, we're mostly concerned with radiation's effects on materials. So our specific considerations are as follows. Neutron properties. We want to keep our neutrons within the fuel, making more fission reactions, or in our control rods, stopping the fission reactions, depending on what our objective is at the time, what operational condition we're in. So, for example, the control rod, we would want a high absorption cross-section, whereas the fuel cladding, we would want a low neutron absorption cross-section, because we don't want it to absorb those neutrons. What else? We've got susceptibility to induced radioactivity. We'd rather our structural materials not be activated or be active at the end of life. So what elements in a material might activate? And what will the half-life of the resulting isotopes be? Will they emit gamma or just beta? And how long will they be active for? What is the half-life? Could we switch off the reactor and just wait for their decay until they're at such low levels? You'll recall that from our last lecture that cobalt-60 is something we really want to avoid because of these concerns. And finally, radiation stability. So, as radiation leads to many weird and wonderful phenomena, including the formation of voids, catastrophic embrittlement, radiation-induced creep. Radiation-induced creep is creep at temperatures where you would not normally expect creep to occur, but it occurs because of that radiation. And they're the sort of considerations that must be covered when choosing a material for application in a nuclear reactor. And throughout the rest of this course, I'm going to look at those key components and how such concerns play a part in deciding what materials are chosen. And what I've given you is a handy table on the preceding page, summarising the main requirements of some of the key components and the potential materials for selection, to now give you a basic introduction in preparation for looking at each specifically. Okay. Now you'll notice the moderator component because I skipped a page in the notes, and that is on the sort of different components in the reactor, because this is what we're going to be focusing on for general reactors in the preceding part of the lecture. Obviously you've got the fuel. It's going to be the first thing we're going to look at, and that's going to be our next section. Well, the fuel can be metallic, alloy, ceramic. It's normally contained within tubes of a metallic alloy as well, so that's called the cladding that holds the fuel in place. And that cladding needs to provide mechanical support to the fuel and prevent the fission products from leaving the fuel element, and also protects the fuel from corrosion from the coolant on the outside. And that fuel's got to be, fissile, doesn't it? So we know that uranium-235 is going to be one of the key elements that we're going to consider. And what is the most common is uranium oxide. And you can use enriched uranium oxide as your fuel, and we'll look at that. That's a ceramic. And we'll look at that in more detail later on. You've then got the moderator, and the moderator slows down neutrons. Remember that the cross-section changes as a function of the neutron energy, and we want the likelihood of a fission event to increase. So in order to do so, we've got to slow down neutrons in a thermal reactor to sustain the fission reactions. And that's what the moderator does. You'll have fuel surrounded by a moderator that is then surrounded by a reflector. And that reflector does exactly what it says on the tin. It reflects the neutrons towards the core and reduces neutron leakage, basically, from the core. And that then improves neutron economy. You'll have shielding outside the reactor as well to absorb any gamma rays, for example, or neutrons. And gamma rays and neutrons need different forms of shielding, which we'll talk about